First thing we're going to do is we're going to talk about how to find the initial value, the rate of change, and the linear equation from a table. So first of all, the initial value is technically the point where the graph is crossing the y-axis. And within a table, it can be found really right there, 0, 5. So what that would mean is if this was a graph right here at 0, 5, this is where the graph would be crossing the y-axis. So what we are inputting for the initial value is not that entire ordered pair, but just the y value. So that would be 5. Now, the rate of change is the ratio comparing the change in y to the change in x. So if we just start the table down here, we don't have to write the whole table, but we'll write the first few ordered pairs. And we were finding the change in y over the change in x. We're technically trying to figure out, well, if we, as far as the y values go, if we go from 5 to 7, we are adding 2. So the change in y is positive 2. And to go from 0 to 1 in the x values, the change in x would be positive 1. Well, the ratio of positive 2 to positive 1 simplifies to positive 2. And when we put those two things together, our linear equation would be y equals 5 plus 2x, where that right there is the initial value, and the rate of change, which we will eventually call the slope, goes right there. So y equals 5 plus 2x. So much like the previous problem, the initial value is where a graph of a linear function will cross the y-axis, and the rate of change is the change in the ratio of the change in y to the change in x. But sometimes we have a table where that initial value is sort of skipped. So what I'm going to do is I'm going to leave a blank ordered pair right there, and we'll write down 1, 9 and 2, 13. Well, the change in y here is positive 4. So the change in y is positive 4 over the change in x is positive 1. So we know that the rate of change is positive 4 because the ratio of positive 4 over positive 1 is positive 4. But what we're going to need to do here is what I call the backwards method. So we're going to work backwards to get to our initial value. So we need this to be 0, so that means we worked backwards 1. In other words, we're just going the opposite direction as if we were going down the table. So going downward table, the change in y was adding 4. So to go backwards, we're going to subtract 4. So 9 minus 4 is 5. So it looks like we have an initial value of 5. And putting that together in a linear equation, our linear equation would be y equals 5 plus 4x. Sometimes when we're dealing with linear equations, we're given an equation and we're asked to graph the equation. Well, much like within tables and we were converting to equations, we can sort of work backwards. So that value right there is our initial value. That tells us where our graph crosses the y-axis. And this -3, and we do have to take the sign in front, is our rate of change. So what that means is that we have a change of -3 in the y direction for every +1 in the x direction. And the reason why is because the ratio of -3 over +1 is -3. So we're going to go downward 1, 2, 3, and an x value change of +1. And so that would be where our next point would be right there. And then we could use the line tool to draw a line through there like that. So that would be graphing a linear equation where we would state the initial value and the rate of change. There are times where we're given a linear equation and we're asked to graph where we aren't asked to find the initial value or the rate of change, but we do have to think about them. And then instead of being one quadrant, it would be two quadrants. So the initial value here is, of course, 5, that value right there. So that means the graph is going to start right there at +5. And then our rate of change is at +4. We do have to take the sign in front. And so if the rate of change is 4, that means we have a change in y value of +1 over a change in x value of, +4 for the change in y value over the change in x value of +1. So we would go up 4 over 1, and that would be our next point right there. And using the line tool, it will automatically draw the line through there. So that's how we graph, thinking about the initial value and the rate of change in 4 quadrants. Sometimes we're given graphs that we can tell by the x and y axis that there is some context to this problem, and we're asked for initial value, rate of change, and equation. Well, we can see from the graph right here that the initial value is 29. Because our graphed line is going in the downward direction, we automatically know that the rate of change has to be negative. Lines that go uphill from left to right have a positive rate of change. Lines that go downhill from left to right have a negative rate of change. So what we have to do is we have to find 2 perfect ordered pairs. So there's one, and it looks like another one is right here. And so from there, we can find our rate of change. So we're going downward 2 and right 1. So our ratio of change in y to the change in x is -2. So that means our rate of change is -2. And then from there, we can put both things together. We can look on our axes to make sure we're using the right variables. Y equals the initial value and then minus 2x, and we can see right there we are using x. There are times when we're given graphs where we're only asked for the rate of change. So to find the rate of change, we've got to locate 2 perfect ordered pairs. So here's one. Looks like here is another. We can see that our line is going uphill from left to right, so we know our rate of change has to be positive. So to go from 10 up to 30, that means we have a change in y of +20, and then we're going from 0 to 1 right there, and so the change in x is a +1, and the ratio of +20 over +1 simplifies to +20. So we know our rate of change is +20, and from there, we would need to look at our axes for the units. So it's always this unit per whatever this unit is talking about right there. So in this case, it would be 20 newtons per second.